Everything around us has a temperature. Your coffee, a glass of water, the room you're in, even the planet itself. It all seems super complex, right? But what if I told you it all boils down to one single, really elegant rule of balance? Let's get into it. So, have you ever really thought about this? You put a hot mug of coffee on your desk and it gets cold. You take an iced tea outside on a warm day and it heats up. Now, these feel like total opposites, don't they? But they're actually just two sides of the very same coin. And that coin, well, we can call it the golden rule of temperature. Because at its heart, it is all about one simple idea: balance. And once you get this, you'll start to see how temperature works absolutely everywhere, from your kitchen all the way out to the cosmos. Okay, so there's a fancy scientific name for this state of balance. It's called thermal equilibrium. It's a really simple but powerful idea. An object's temperature is only going to stay constant when the energy flowing in is perfectly matched by the energy flowing out. You can think of it like a perfect stalemate. So, here's the crucial point. This is the whole thing in a nutshell. There are only two states an object can be in, period. Either it's in balance, energy in equals energy out, and its temperature holds steady, or it's in a state of imbalance where those two aren't equal and its temperature has to change. It is that simple. Okay, so if balance means a stable temperature, the obvious question is, what happens when we tip the scales? Well, this is where things get really interesting, because this is the fundamental physics behind all heating and cooling. An object heats up when it's soaking in energy faster than it's getting rid of it. Let's go back to our iced tea on that sunny day. It's absorbing heat from the sun and the warm air all around it way faster than its own coolness is radiating away. So, with more energy coming in than going out, its temperature has no choice but to go up. And of course, the exact reverse is true. An object cools down when it's losing energy faster than it's gaining it. That's our hot coffee. It's just radiating its heat out into the cooler air of the room. Since way more energy is flowing out than is flowing in, its temperature drops. It's just perfect symmetry. Okay, so we've seen this rule works for our drinks. It's neat, it's tidy, but what if we zoom way, way out? What if I told you this exact same principle of balance is what governs the temperature of the very ground beneath our feet and the air we breathe? Let's scale this up. Because believe it or not, our entire planet is constantly performing this giant balancing act. Earth, too, is always seeking that state of equilibrium, trying to keep its temperature stable by balancing the energy it gets with the energy it gives away. So, what does this energy budget look like for our planet? Well, the energy in part is pretty straightforward. That's the incoming radiation from the sun, the stuff that warms our planet. The energy out is the heat the Earth itself gives off, radiating that energy back out into the cold vacuum of space. So, for Earth's average temperature to stay stable, these two forces have to be in balance. Just like the source material says, the energy it receives from the sun must be balanced by the energy it radiates back into space. It's the exact same golden rule we saw with our cup of coffee, just on a massive planetary scale. So let's just put this all together. The main thing to remember is that a steady temperature for anything requires a perfect balance of energy in and energy out. The moment that balance is tipped one way or the other, the temperature has to change. And the most amazing part is that this simple, powerful rule applies to everything, from a drink on your table to our entire world. And that leaves us with one final, pretty crucial thought. We've seen that the temperature of our entire world hinges on this incredibly delicate balance between the energy coming in and the energy going out. So the question we have to ask ourselves is, what happens if we're the ones who tip the scales?